All right, hi everyone. Thank you very much for joining us in this Q-Farm seminar. It is with great pleasure that we welcome Tomas Jochym-O'Connor to give the seminar this week. So Tomas did his PhD at Waterloo around the same time that I was doing my PhD in Waterloo. And he was doing his PhD with Raymond Laflamme in error correcting codes. After that, he went and did a postdoc at Caltech with John Preskill. And now he's working at IBM in New York. And so today he'll be talking to us about some of the work that he's been doing in quantum error correction. So without further ado, Thomas, take it away.
Yeah, thanks JP. Thanks for the introduction. I'd like to start by, first of all, yeah, it's great that we can have this online seminar, and it's great that this is being put together. And I think JP kind of went over what the question protocol has been in the past. So feel free to write any questions in the chat, and I'll try and periodically go look at them, or JP might interrupt me if there's a pressing question. But yes, I know that Q-Farm encompasses many different researchers from different backgrounds, and I was told that you know, because there'll be different people attending from different backgrounds, to try and make it accessible, at least at the beginning. I'm gonna kind of ramp up. So at the beginning, I'll be pretty introductory about quantum error correction, and in particular about stabilizer codes, and then talking about logical gates. So if there is something that's not clear or that needs clarifying, please, I do welcome questions, because I want to make this as enjoyable for everyone. Okay, so yeah, so here's a bit of the outline of what I'll be discussing. I'm going to give a review on error correction, and in particular in stabilizer codes, because that's the formalism with which these results pertain to. And then I'll discuss a little bit about how we, on the theory side, think about performing logical gates in a fault-tolerant way, and what are the models for fault tolerance that we have. And then I'll introduce this notion of disjointness in stabilizer codes, which is an algebraic quantity, which we'll use to put restrictions on the logical gates that we can perform in the code, in particular in this fault-tolerant way. And then I'll kind of go over, towards the end, I'll summarize some implications of these results on disjointness and what they apply for error correction as a whole, and present some open questions with regard to that. Okay, so I don't think I have to go through too much of a motivation for this crowd, but I mean, the reason we consider error correcting codes is, as we all know, nature is inherently noisy. And I mean, this is even true in the classical setting. You know, there are classical error correcting codes as well that are used in our everyday devices, but also in particular, you know, are very actively used in things like communication, classical communication, which has a high rate of noise. And in the quantum setting, you know, if we're going to be implementing these large depth circuits to do all our nice, exciting algorithms, we're going to need to reduce our logical error rates to be very low, and that requires some form of protection and error correction, and more in particular requires a notion of fault tolerance, so that errors are going to happen in our system, but we would like to be able to control them, correct them, and then continue moving on with our computation, so that it's, you know, we can, the length of computation, it shouldn't really, you know, we should be able to reduce our error rates to be sufficiently small so that it doesn't matter what length of computation we want to implement in theory. And when we think about fault tolerance, usually how it's thought about from a theoretical perspective is that we piece together a bunch of short circuits, because the idea being is that if you can make this small component fault tolerant so that the errors don't propagate too badly, then if we piece all of these together, and every time we're kind of controlling how much the errors are propagating, we can keep the numbers of errors small throughout the whole circuit. So the high level idea we should have in mind is when you're running your the gates in your quantum algorithm, you know, if you have some factoring algorithm or whatnot, each one of those gates, you know, you're running some small sequence of operations on your physical device, and then you're doing some sort of checks to correct for the errors, you know, control them. Then you might do a few more gates, check again, and you're continuously doing this back and forth about actually manipulate, you know, doing your computation and checking your computation at the same time. So that's kind of the high level perspective we should have in mind. And so kind of the simplest, I don't even want to really call it a quantum error correcting code. This is really a classical code. Is the 3-bit repetition code, where you encode your 0 state and your 1 state just by repeating multiple copies of 0 and 1. And then you can just map out what the different X errors on each qubit will map to in the corresponding state. And it's pretty clear that if, you know, say in the 3-qubit repetition code, you have a single X error, in order to correct for that error, what you need to do is do some sort of majority vote and just count what is the largest numbers of zeros, and are there more zeros or ones? And if there are more zeros, then this was a logical 0 state. If there are more ones, there's a logical 1. Now, the important thing for quantum error correction is that we actually don't want to measure individual qubits because we don't want to project, you know, we're going to have states in superposition, and we don't want to project onto the 0 or 1 state necessarily. We want to maintain those superpositions and not decohere the system. And so when we're measuring doing this majority vote, we're actually going to measure parities of bits, and we're going to infer the information from the parity of the operators. So if we wanted to know if one of these X errors occurred on our 3-qubit state, we would measure ZZ on the first 2 qubits and ZZ on the second 2 qubits. And then depending on whether if we get a plus or minus 1 outcome of these measurements, that will tell us which of the errors, these single qubit errors, occurred. And you can just check this by, you know, checking which of the errors anti-commute with these parity measurements that we're applying. Okay, so if you had some X1 error, that's going to anti-commute with Z1, Z2, but it's going to commute with Z2, Z3. So the syndrome of measuring -1 for the first measurement and +1 for the second measurement would tell you, okay, you have an X1 error, let's correct it. So this of course only works if you have a single error. If you have multiple errors, then this protocol will fail, but just a simple example. But of course, this code is useless against correcting its phase errors, because any phase error on any of the 3 qubits will result in a logical error. And this can be seen from the fact that any Z error commutes with our parity measurement, so that we can't infer any information about the Z errors from just measuring these Z operators. However, this code, even though it's a classical code, it is an example of, in the quantum setting, of what we call stabilizer code. So we had some code space C that was whose basis of states were this all 0 string and all 1 string. And this is the eigenspace of these Z operators, as I said. So our code space is the +1 eigenspace of Z1, Z2, and Z2, Z3, and any product of those operators. And this can be generalized for any commuting set of Pauli operators. So, and this is what we call, if you take this group formed by the product of all these commuting set of Pauli operators, P1 through PL, this denotes a stabilizer group. And we can define a code to be the code space to be the set of states that are the +1 eigenstate of all of the generators from our stabilizer group. And because they're all commuting, we can satisfy that requirement that's in the +1 eigenspace. And so this is what we define as a stabilizer code. And again, detecting and correcting errors involves just measuring these stabilizer generators. So in the previous example, we measured Z1, Z2, and Z2, Z3. Now we would just, if you had some commuting set of Pauli operators, you just measure these Pauli operators. Your outcome is going to be either +1 or -1. And depending on which of these outcomes are -1, you're going to infer, okay, maybe this error occurred, and then correct it. Because the error is any error will anti-commute with some subset of these stabilizer generators. And determining which error occurred, this is a decoding problem, and I won't really touch on that in this talk, but there are known methods depending on the code. Okay, so maybe just to give one more example of a quantum stabilizer code, truly quantum code is this 4-qubit error detecting code where the stabilizers are the all x tensored on all 4 qubits, and z tensored on all 4 qubits. And now it's fairly obvious that any single qubit Pauli error will anti-commute with one or both of these operators. And so any single qubit Pauli operator will take you outside the code space and can be detected by measuring these stabilizers. However, we won't necessarily be able to correct it because it's a distance 2 code, but for simplicity, let's just talk about detecting these errors. And so this can detect any single qubit error. And why are we only focusing on Pauli errors and not some more general form of errors? Well, that's because these Pauli errors form a basis for permission operators. And so if we think about the noise channel, it can always be parameterized in terms of these Pauli errors. So if it is sufficient, is necessary and sufficient to be able to correct for these Pauli type noise in order to preserve our code space. So if we can correct for all single qubit Pauli noise, then we can correct for all single qubit errors in general, for example. And the same thing would be true for multi-qubit errors. And kind of one final note on these stabilizer codes is that the logical operators, so the logical Pauli operators, that is our encoded Pauli operators, are Pauli operators that commute with all the elements of the stabilizer group, but are not in the stabilizer group itself, right? So for this 4-qubit code, as I write on the final line here, you can see that any weight 2x or z operator is going to commute with this all x or all z stabilizer, but clearly they are not themselves a product of the all x and all z stabilizers. So they're not in the stabilizer group themselves, but they commute with the stabilizer group, and so they will form the logical Pauli operators. So here we have 2 logical Pauli operators, x1, x1, x2, z1, z2, and you can check that they form the appropriate commutation relationships between them. So x1 anti-commutes with z1, but commutes with z2, etc. Okay. So next I'll start talking a bit about the surface code. Maybe I'll just make sure that there were no questions for this first part. Okay. Continue going on. And okay. So probably the most well-known stabilizer code is the 2D surface code or Tor code. And this is defined on a 2-dimensional lattice. Are you guys seeing this? Is it changing? That's weird.
Yeah, we are. I'm not sure what's going on.
I'll just go back into slideshow. Okay. Oh, that's so strange. I don't know why this is happening. Let's try something else. Okay, hopefully that holds still. Probably the most well-known stabilizer code is the 2D surface code or the Tor code, which is defined as follows. So you have some 2-dimensional array of qubits, and you place all the qubits on the edges of this square lattice, and the Z stabilizers are defined as, sorry, I'm going to back up here. Yeah. The Z stabilizers are defined on the plaquettes of your code, and the X stabilizers are defined on the vertices or star operators. And as it's clear that all the Z stabilizers and X stabilizers commute because any plaquette and any vertex will intersect at either 0 or 2 locations. So they commute. So this forms a commuting set of Pauli operators that define your stabilizer group. And we can also think of this in terms of a Hamiltonian, where you just write any stabilizer code we can think of in terms of its stabilizer Hamiltonian, where you write it as the sum over all the stabilizer generators in your code. And the ground space will be formed by the ground space of this Hamiltonian is the code space of your code. That is the +1 eigenspace of all of these operators. And now we can think of errors as excitations in this ground space of the Hamiltonian. So if I had some X error on the qubit that is red here, that anti-commutes with the 2 neighboring plaquettes, Z plaquettes. And we can think of these 2 plaquettes that are violated as anionic excitations in your code. So if you had a single error, you would have to give rise to these 2 -1 syndromes. If you had a pair of errors that were next to each other, the only plaquettes that would be violated are at the endpoints of this error string. So give the following syndrome. And if you just continue this process, if you kind of had a longer string, you still only have violations of 2 plaquettes at the endpoints, because any of the other plaquettes, they intersect this error twice, so they commute with this operator. So I can continue this process and draw a kind of longer and longer chains. And you see if you wrap it all the way around and close the loop here, then this closed loop will actually commute with the stabilizers of your code. So this is a logical operator, but it's actually going to be the logical identity because it's formed of, you can take the product of the X stabilizers of your code and get this loop on the lattice. So this is actually in the stabilizer group, and it gives you a nice interpretation of what the ground space of the stabilizer Hamiltonian are. They're actually the superposition over all closed loops applied to the all 0 or all 1 qubits in your code. So if you take the superposition over applying closed loops to all 0 or all 1, you get the logical 0 or logical 1 state in this code. And the logical operators are going to be formed from non-contractible loops. So if we think of this as either a lattice with closed or open boundary condition, so if we had periodic boundary conditions, then the logical operators would just be the non-contractible loops that go around this torus, or we can put some sort of boundary conditions, and then it would be connecting, the logical operators would be connecting 2 boundaries on the opposite side of the lattice. So you have in this example, you've got the Z logical operator would be vertical and the X logical operator would be horizontal, and you notice they anti-commute because they always intersect at a single lattice point. And kind of importantly is, that will be important for later in the talk, is that there are many different representations of the various Z and X logical operators, because you can multiply them by the stabilizers of your code, these phase or plaquette, these plaquette or star operators, and shift them, kind of deform them and shift them in your lattice. So this Z prime is equivalent to the other Z logical operator, and this X prime is equivalent to the other X logical operator. And you'll notice that Z prime intersects with either X or X prime also at a single location. So it preserves the right anti-commutation relations. Okay, so kind of the upshot is that these, at least from the important thing to remember for later in the talk, is that in the 2D surface code, you have logical Pauli operators that are formed from these non-contractible loops. And each one of these Pauli operators, logical Pauli operators, there are many different representations, and any vertical or horizontal loop will form that connects the two opposite boundaries will form a logical Pauli operator.
So I have a quick question just before you go on. So can you somehow tailor the types of logical operators to be robust to different types of noise by picking different loops or different configurations on this space, or are they robust to the same type of noise?
So maybe I'm not quite following. So are you saying like if you have some biased noise model or?
Okay, well, maybe another way to ask it is, why would you want to, pick different configurations of logical operators, like different loops in your graph here? What does that advantage give you?
Well, I mean, I guess it can go both ways. I mean, this is really just a product of encoding your logical operator. There's some degeneracy in how you choose your logical operators in your code. And this is going to be true for any code, any quantum error correcting code, but this just, in this topological setting, it has this nice interpretation, like visual interpretation. But I guess kind of how you could use that to your advantage is if you had like some patch of qubits in the middle of your code that were very, that you knew were bad or faulty. In a certain sense, you could cut those qubits out of your code and just like not think of them in your code, and still encode the information in the rest of the code. Depending, you have to choose special boundary conditions on those qubits. But you'd still get the important thing is that you get protection from the topological aspects of the code. So the fact that you have these macroscopic logical operators. So as long as you chose your boundaries correctly and then get some defective area, you can kind of work around that defective area, let's say. So that could be an advantage in this setting. Is that you could have like these faulty locations, and that not be a problem. It's not like if one location fails, you're done. But you just have to know about them. Yeah, but there are going to be other, part of what I'm going to be talking about later in the code is that the fact that you have these different representations are going to, when you're thinking about logical gates, you actually have to think about how the action of the logical gate interacts with all of these different representations, and that's going to impose some restrictions. Yeah, so that leads nicely into discussion about logical gates. And before I talk about fault-tolerant components of logical gates, I just want to give a little a few more slides on background into the Clifford hierarchy. And so suppose you had some unitary that is going to be a logical unitary on your code space. You can do some simple algebra to see the following: is that if you have if U is transforming some code state psi, so I put over the bar to indicate it's a logical state, transforming some psi into phi. Well, since psi is in the code space, you can multiply it by any stabilizer and it remains invariant. And then of course, since U is a unitary, you can put in a U dagger in U. That's just identity. And so then you see that this U, if you sandwich any stabilizer, any element of your stabilizer group by U under conjugation, this should also leave the code space invariant, because this is this will return the code space. So it's the state phi in your code space is a +1 eigenstate of US U dagger. And so that means that U has to preserve, it has to be an identity operation. And also the logical action of your gates will be the action of U on the logical operators of your code under conjugation. So you can fully understand what the logical action is by considering the action on the logical operators. And this is really to motivate that when we're thinking about logical gates, we should always be thinking about its action on the Pauli operators, stabilizers, and logical operators under conjugation. And this is what motivated this notion of the Clifford hierarchy, to understand what a gate is doing and how it's transforming certain operators. So the Clifford hierarchy is defined as follows. The first level is just the Pauli group. And the nth level it maps the Pauli group to the level below it, the m-1 level. So, for example, the second level is all unitary operators that map Paulis to Paulis. And these are just known as the Clifford operators. So the third level would be all unitary operators that map Paulis to Clifford operators, and etc. You can generalize this to higher levels. And for universal computation, Clifford operators are classically simulatable, but if you had the Clifford operations plus any gate in a level higher from the Clifford hierarchy, so third or above, then this is sufficient to simulate universal quantum computation, assuming you had the full Clifford group. And an equivalent definition, is very easy to see, is that the nth level of the Clifford hierarchy are the set of unitaries such that this group commutator is in the m-1 level. This is just by multiplying by a Pauli on the inverse Pauli on the right, which is just the Pauli itself. And that it's fairly straightforward to see that that won't change which level you're in. Okay. But the definition that's going to be useful for our purposes is this idea of nested commutators. So we can rewrite the definition I wrote on the previous slide of the nth level of the Clifford hierarchy in terms of nested commutators. And this comes from the following observation, is that if you look at, if U is in C1, so that U is a Pauli, if you look at the group commutator of two Pauli operators, then this is just going to always be equal to plus or minus the identity. Now, if you had a gate if U is in the Clifford group, then if you look at the group commutator of U and P, that's going to be equal to some Pauli by definition. So then if you nest that one more time, so this U and P2 is some Pauli, and if you take the group commutator with another Pauli, this is going to be equal to identity. So in general, the mth level is when you take this nesting m times and you're equal to the identity. So if U is some unitary operator such that for any choice of Paulis, when you do this nesting m times, you get plus or minus 1 the identity, then that implies that U is in the mth level of the Clifford hierarchy. Okay, so this is just, I know I kind of went quickly through that, but that's just to keep in the back of your mind. This is the definition of the nth level of the Clifford hierarchy that we'll be using moving forward. Okay, so just generally speaking, when we're thinking about fault tolerance, what are the type of gates that we tend to focus on? Again, on the theoretical side, well, there are three types of fault tolerant operations that I like to think of. The first is a transversal gate. So the idea behind a transversal gate is that you implement your logical gate by addressing each of the qubits of your code individually. And the really nice property behind that is that if you have some error pattern, which I've drawn in red here, and you do some transversal gates, so you're doing some operation on each individual qubit, then your errors, while they may be transformed on the single qubit, they remain, they don't spread. They remain local on those individual qubits. So obviously this is very desirable because errors don't spread under transversal gates. And so this is a naturally fault tolerant set of gates. Another set of gates that can be made fault tolerant are geometrically local gates. So again, if we're talking about some topological code where you have some notion of geometric locality, then if your gates were all geometrically local as well, so let's say you had some interleaving of 2-qubit operators, so the 2-qubit operator could spread the error locally like this, and now you say you had some other set of 2-qubit operators, it could again spread the error locally. So this red error is growing. When you continue this process, you can see it grows, but it always grows locally, right? It can't grow too fast because all of your errors are, your circuit elements are local in this grid. So it doesn't have the ability to grow quickly. And so if you compose many of these geometrically local gates and then periodically check for errors, you should still have some notion of fault tolerance because errors can't spread too quickly. And the third The third set of gates are not quite as, are definitely not as good as these other two, because errors can spread more quickly, but as long as the depth is kept short enough, then things should be okay. And those are constant depth circuits. So here I'm not imposing any sort of restriction on the connectivity of your circuit. So you could have some random connection of 2 qubit gates, say, and your errors might spread. So this single error spread to 2, and now you have some other set of connections, and these 2 errors can spread to 4 errors, and these 4 errors can spread to 8 errors. So you get this exponential growth in terms of the errors. However, if you keep the depth of your circuit very constant, then that 2 to the constant is still some constant. And so as long as you had very few errors at the beginning of your computation, it will result in hopefully a controllable set of errors. And when I'm talking about constant depth here, I'm always kind of keeping at the back of my mind that you have some family of codes with growing distance, so you can handle more and more errors. But the depth of the circuits you're considering are not growing, so they're remaining small. And in theory, this could be handled by your code as long as that was the scenario. And so what this work is going to try and focus on is providing some bound on these constant depth circuits. Because so far the bounds on logical gates that we have are mostly in terms of either transversal gates or geometrically local gates, but very little is known about bounding these constant depth circuits. And that's what we're going to be aiming for towards the end of this talk. Okay, but first, the nicest of the set of gates that I talked about in the previous slide were these transversal gates. And so you might say, okay, why don't we find a code where we can do all our set of universal gates in a transversal way? And this is impossible due to this famous, what people refer to as the Heesink-Nil theorem, that states that there's no error correcting code that exhibits a set of universal transversal gates. So you can't have both universal quantum computation and transversal computation as one. So you need some additional non-transversal component in order to get a universal set of gates. And the reason behind that is that any transversal gate will only be able to generate some finite size group. But you can still do a lot of things with some short depth circuits. And I'll just give one example of a short depth circuit in the surface code, that will allow you to implement the Hadamard where you wouldn't be able to do it in a transversal way. So the Hadamard maps X to Z and Z to X under conjugation. So if you applied Hadamard just naively and did it transversally, you would change all of your, so this is applying Hadamard, you would change all of your X stabilizers to Z stabilizers and Z stabilizers to X stabilizers. And now your X stabilizers would be defined on plaquettes and your Z stabilizers would be defined on the vertices, which is a different code. So even though you've swapped the X and Z logical operators, you've kind of rotated your code. But in order to kind of get back to the correct orientation, you can do this long range swap along the diagonal, which kind of just folds the code across itself. And it allows you to rotate the code back into its original configuration. And so a combination of this transversal Hadamard and long range swap, this depth 2 circuit allows you to implement a logical Hadamard. Okay, so the kind of inspiration for our work was this work by Bravi and Koenig from earlier this decade, where they characterized the set of logical operators that you could be implemented with geometrically local gates in a topological code setting. So I'm going to go over their argument, and because this is really the inspiration for our argument for non-local gates, and it'll give you a good flavor of how we use these group commutators. So I'm just going to go over the argument for the 2D surface code, even though it generalizes to all topological codes. So if you have some 2D surface code, we'd like to characterize what can we do with a short depth local circuit, so geometrically local circuit U. And we would like to know what logical gates can we implement in such a setting. And like I said, in order to understand what logical gate you're implementing, it's sufficient to study the action of the group commutator on the logical operator. So if you have some logical operator U and you had some logical Pauli operator, we're going to focus on, say, Pauli Z here. You can just consider what is the action of this local operator on Pauli Z. And by looking at the group commutator, so say I had this sequence of 2-qubit gates, well, you can kind of ignore all the 2-qubit gates that don't overlap with our logical operator, because in the form of this group commutator, the U, wherever there's no support of this logical P, the U and U daggers will cancel out. And so you can kind of get rid of all the other gates and just focus on the ones that overlap with our logical operator. And what that ends up doing is, shifting it or spreading it locally. So you had some vertical logical operator and you kind of spread it out locally. And you can kind of think of this abstractly as you're smudging out your logical operator. So the support of your logical operator is now, it's again going to be this vertical band, but this band is now just a little bit wider than it originally was. And I said, okay, in order to understand the action of this, what logical operators can be encoded in such a band, we have to consider its action in this nested commutator fashion, the action that this operator now has on another logical Pauli operator. So let's take the horizontal X operator and see what is the action of the group of the group commutator of U and P on Q. So this operator Q is the X operator. So again, we have to focus on where they intersect, and they're going to intersect kind of on this wherever they overlap. So this narrow band that I've encircled in red, and this area blue is it's a constant depth local circuit that only acts on this blue area. So what it can do is it can spread out this red band, but only within the confines of the blue operator. So it's going to kind of fan things out along the blue operator, and so you get this region of support where this group commutator can be supported. So this now is some operator that is acting on some closed region in our 2D surface. Remember, I told you, when I was talking about stabilizer codes, that closed regions that don't form non-contractible loops. So this is some contractible region in the 2D, on the 2D surface code. This cannot support any logical operators. The only logical operator it can support is the identity operator. And so this group commutator must be equivalent to the logical identity. And so if this group commutator is equivalent to the logical identity, by the definitions of the Clifford hierarchy, the operator U itself must be a logical Clifford. And so this is an argument to say that any constant depth local circuit U can only perform a logical Clifford operator in the 2D surface code. Okay, and the key ideas here, and so their general statement is for general 2D topological codes, this will be true, that you can only perform logical Clifford gates, and they generalize it also to higher dimensional codes, 3, 4 D-dimensional codes, and you'll be in the Dth level of the Clifford hierarchy there. But the important assumptions is that you were not only constant depth, but you had a set of geometrically local gates, and that corresponded to the smudging out of the operators. And the question we aimed to answer was that if you had a similar structure, but now rather than only having geometrically local gates in these topological codes, what if you had non-local unitaries? So what if you were allowed to it would still be constant depth and a short circuit, but allowed to couple qubits arbitrarily in your lattice? Could you get something more? Because this would still be, you could still imagine notions of fault tolerance here, but you'd no longer be bounded by the the restrictions of their theorem. So again, we're going to be focusing on this group commutator, but now the setting is that your circuit can couple any qubits in your code. And I'll focus again on the 2D service code. So we're going to study again how it propagates what is the propagation of the action of U on some logical operator P. And so we can ignore all of the components of our circuit that don't overlap with our logical operator P. So that are these yellow components here. So we'll only focus on the blue, and that spreads our logical operator along the support, potentially spreads it along the support of the blue operators. So if we had originally some logical operator P that had some support on D qubits, where D is the length of the code, then after the action of this logical operator, it spread that support to, it could have grown it by some constant factor, but still the support is bounded by some constant times D, okay, if the circuit is short depth. And now the key is we know that, as I discussed previously, if you look at say the X logical operator, but this will be true for all the logical polys, we have different representations of the logical poly that are all disjoint from one another. And so you can represent a logical X by some horizontal band, but it could be any choice of horizontal band. And each one of these horizontal bands are disjoint from one another. And like I was saying, the action of the gate has to be equivalent on all of these different logical bands. So we can study the group commutator on our choice of which of these representations we choose. And because the original support of the group commutator between U and P, like I said on the last slide, was some constant times D, there has to be at least one of these representatives of X that only overlaps, because they're D disjoint representatives of them, there has to be one that only overlaps with that most C of the locations of the group commutator of U and P. So basically what I'm saying is that, you have the spreading of the operator P by these blue gates, that we can always find one of the green operators such that the overlap is very small with the spreading of the blue. And so importantly, if you then study, if you have some short depth circuit, and you have some operator A, or in this case, X, that is transversal, it's the product of all X, then the support of this operator under some local circuit is limited. It can't grow too much. And it's limited by the overlap of the supports of the operator itself and the circuit. So if the support, basically the upshot is that if the overlap of our logical X is very small and is bounded by C with respect to our circuit, which is given by the group commutator of U and logical P, then the support of this nested group commutator actually has to be small, and it has to be smaller than D, where D is the distance of the code. So it has to form a correctable region. And thus it implies that this group commutator, this nested group commutator can only encode the logical identity. And so just like we had in the case of local circuits, this unitary can only perform a logical Clifford gate in the 2D surface code. Okay, and a similar type of argument, I only argued for its action on Z and X, but a similar type of argument will hold for all Pauli logical operators. And so this is a way of, and the key element of this was that you had all of these disjoint representatives of the X logical operator. So you could always find one that had very little overlap with the group commutator U and P, this operator that's represented by the group commutator of U and P. Okay, and so the upshot is that even for non-local circuits, if you're short depth any unitary acting on any such unitary acting on the 2D surface code can only encode a logical Clifford operation. And so in our work, we generalize this notion of disjointness because to account for, certain, for example, the Y logical operator in the 2D surface code, it always overlaps. There's always some overlap, but it's limited. So you can kind of refine this notion of disjointness and still recover the results. This is this idea behind C disjointness, but it's kind of technical. I won't really focus too much on this. But just to say that, this argument does generalize to the other logical poly operators, even the Y logical poly operator. And so we can define this general notion of the disjointness of a code is the minimal disjointness over all logical operators of our code. So if we we care about if we want to say what is the disjointness of a code itself, then we take all logical poly operators G and we look for the disjointness of all of these different operators, and we find which one of these is false. Okay, and this maximization over C, this is again reference to the last slide, but it's not too important. But okay, so disjointness characterizes kind of this idea of like how many different representatives are disjoint from one another of the different logical operators. And in a very important fact, and this is kind of coming back to JP's question earlier, there's always, because we have some degeneracy in terms of the logical operators, it's fairly natural to think that for any non-trivial code, so that is any code whose distance is greater than 1, you're going to have some disjointness. You'll be able to find some disjoint set of logical operators such that they minimally overlap. So there's this if and only if statement that if the distance is greater than 1, so you have some non-trivial code, you always have a disjointness that is greater than 1. And so we prove this general result where for transversal gates, so let's focus a little bit more on transversal gates, and I'll come back to constant depth, general constant depth gates in a second. We prove this general result for that ties together the notion of disjointness and what gates are achievable, but what transversal gates are achievable for a given code. So if you have D as the distance of your code, and D up is the largest distance, we call the max distance, which is the largest distance of a logical operator. So it's kind of like the largest support of, if you look at all logical operators and look at their distance, some of them might be larger than others, and the max distance is the largest of such operators. And basically what it says is that if this inequality is satisfied for some value of M, then any transversal gate has to be in the mth level of the Clifford hierarchy. Okay? And what are the implications of this result? Well, so we know that, as I said a few slides ago, the disjointness is always greater than 1. So this on the right side of this inequality, it's always growing as a function of M. However, if I give you a code, then just a particular code, then the max distance and the distance, those are fixed for your code. So if given a particular code, given the fact that the max distance and the distance are fixed, there will always be some value of M such that this inequality will hold. And what that means is that any transversal gate has to be limited in some level of the Clifford hierarchy. Maybe it's a really high level, depending on your parameters D up and D, but it's limited to be in some level. And what that says is that because when you compose transversal gates, it still remains transversal, what that says is that the power of the transversal gate is limited. It can't go into arbitrary levels of the Clifford hierarchy, and thus it can't be universal. So this is just a restatement of the async null theorem, is that when you have a transversal gate, you have limited power, and you can't do arbitrary computation. So, and it's the disjointness here that limits your power. And kind of to highlight the different notions that are going on in this inequality, basically, if you want to have a gate that's very, a higher level in the Clifford hierarchy, you want an asymmetry between the sizes of your different logical operators. So basically, you might want your X logical operator to be large while your Z logical operator to be small, because this will, if you have this D up to be much larger than D, then that helps you violate this inequality. But the caveat is that typically, if you have your Z logical operator, say, being small, it's going to have a greater disjointness. So there's this trade-off to be had between these different notions. Okay. And another implication of this result is that any gate that allows you to move up in the Clifford hierarchy cannot be implemented transversally in a code. And this is in particularly important for the Toffoli gate. So an important property of the Toffoli gate is that you can always compose different Toffoli gates with ancillas to get, so the Toffoli is control, control X. But if you compose different, like in this circuit, if I compose 5 different control, control X with a few ancillas, I can simulate control, control, control X. And so you're always able to add in more controls by adding in extra Toffolis and extra ancillas. But when you have more controls, these are actually higher level gates in the Clifford hierarchy. And you can get to arbitrarily high levels of the Clifford hierarchy by composing these Toffoli gates. And this implies that the Toffoli cannot be implemented. Because this would allow you to get to arbitrarily high levels, that implies that the Toffoli cannot be implemented transversally in a code. So it's a restatement of that result. And kind of one other thing is that this notion of disjointness, it's not going to be typically easy to calculate in practice. Actually, it's going to be quite hard for a given code. But it's good enough to have just a bound on this disjointness in order to be able to say something about what logical gates you can have, right? So if you have some bound on the disjointness, and then you can satisfy this equation for some notion for some bound in your disjointness, and you get that this inequality is satisfied for some m, then that will tell you that you at least have to be at that level of the Clifford hierarchy, and maybe even you're restricted to be lower if your bound is not that good. So that's just to point out that you might not necessarily have to calculate it exactly, but it's sufficient to have a bound to be able to make some statements. Okay. And the kind of final things I wanted to emphasize is that it can help inform you for the types of codes you might want to search for if you're looking for a particular gate. So, and in particular, this is some ongoing work that hopefully will be out soon. As we're thinking, along with my collaborator Ted Yoder, we're thinking about, okay, we would like to get in the traditional 4D Tor code that is used for self-correction, you have a symmetry between the X and Z logical operators, and this kind of enforces that any transversal gate will be a logical Clifford gate. So if we're looking for gates that were in the higher levels of the Clifford hierarchy, we need to exploit an asymmetry between the X and Z logical operators. And so when we're searching for such a code, we emphasize that these logical operators were asymmetric. And the disjointness was kind of the motivator behind that. So it can kind of help guide you towards which codes you want to look for if you're looking for a particular gate. So in this case, we're looking for transversal CC in this case, in this code. Yeah, and you can kind of look at all the popular sets of codes and realize, okay, what are their bounds in terms of their logical operators, and what are their existing known logical gates? Do they saturate these bounds? And we studied that in our code for the Tor code or the Reed-Muller code family. And you can also make some statements about if you're looking for gates that you have a universal set of transversal gates and self-correction, you can make some statements about just loose bounds about what type of code would you need there, but I won't go too far into that. Okay, and the final point I wanted to make is, so I talked a bit about when I was giving my example in the surface code, I talked about we were looking we introduced this notion of disjointness to study the action of constant depth non-local gates. And then I talked about a bound for disjointness in terms of transversal gates, but you can generalize this bound for non-local gates as well. It's just the left side becomes a lot harder to control because you have this double exponential growth in terms of the M and the depth of your circuit. But kind of an important, so that's just to say that this notion of disjointness can be generalized in many ways, but kind of two important open questions that I have with regards to this is, can these techniques be used to generalize this notion of the East-Sink-Nil theorem, which bounded transversal gates? Can we, to being non-universal, I would like to know if there's a generalized bounds for low depth circuits in general. So if you had some constant depth circuit and some family of codes, can you say that, oh, no constant depth circuit can implement a universal set of operations? Or maybe some of the techniques here can be used for that. And if we looked outside the realm of topological codes, that's where we can have the best handle on disjointness, but in general, it's some algebraic quantity. And in theory, we could look at it for any code, and maybe when we apply these results to kind of popular codes in the quantum error community now, these LTPC codes, can we bound what logical gates are obtainable in those codes? Is something that down the line I would like to look at, and it would be very interesting. So just to conclude, the theory of fault tolerance has for a long time focused on transversal gates or geometrically local gates, and we have some good understanding of what gates are possible in those settings, but we aimed in this work to study what can be done. Could we bound the power of non-local constant depth circuits, in particular in these topological codes, but in general, more general codes? And this led to introducing this new quantity that we call the disjointness to classify the gates that are obtainable. And we hope that this will have some other important applications to coding theory in general. With that, I'd like to thank you for your attention, and happy to take as many questions as there are.
Great, thanks a lot, Thomas. So I'll open the floor to questions. If anybody wants to either post questions in the chat or just unmute yourself, you can ask them directly to Thomas. So, okay, so I actually had a question. I was wondering if you could comment maybe more on a general level where IBM is in terms of implementing some of these codes, or what types of codes are they already implementing on their hardware, and where are they thinking of going? Like, what are the next sort of codes that might be useful in 2 to 5 years?
Yeah, I think there have been, in the past few years, there have been experiments in IBM where, again, it's focusing on measuring these stabilizer checks. So again, it's all stabilizer code, and how you fault tolerate. I didn't really talk about this in this code in this talk, but there are particular protocols for measuring these Pauli operators fault tolerantly. And I think the next year, talking 2 to 5 years, they've made no secret that what they envision is, some form of 2D topological code. So some encoding in 2D with some nearest neighbor coupling, implementing something similar to the surface code or torque code. Whether it's exactly the one I presented here or some variant of that, there have been a few different proposals. And there were a paper last year, for example, theory paper, but I think the experimentals are interested in is implementing on a hexagonal type lattice. But they're all, broadly speaking, yes, 2D topological codes, which are very similar in flavor to the surface code. And that's kind of the near to medium term objective. Now, more longer term, I think it's just an open question of research. There are some downsides to the surface code. And if there are other codes that maybe have more complicated connectivity, but have other nice properties like a higher rate or better protection or higher threshold, then I think that could be adapted. But for now, it's 2D.
Okay, great. And is there like some notion of sort of you trial and error? Like you just try a bunch of different codes and see which ones work, or you know, in a directed way, obviously?
Well, no, I don't think it's necessarily trial and error. It's, of course, it's motivated by the noise model and by your noise model, and also what you can manufacture like easily in the lab. So, for example, this hexagonal code that I was referring to, the reason they're focusing on that is that it minimizes the connectivity in your chip. So instead of in the traditional Tor code, you have a connectivity of every qubit talks to 4 other qubits. But in this hexagonal one, you can get it down to every qubit talks to only 2 or 3 other qubits, which makes it easier for in the manufacturing aspect. But again, this is, so there are, of course, this is the nice thing about having a theory and experimental team working the same place, is that you can kind of get this feedback. If they say, okay, this is challenging, how can we adapt it, vice versa. But again, this is still, I would, all of this with a grain of salt, because it's still pretty early days. I think it's, until we start actually implementing these experiments and getting feedback on them, it's hard to know. There is a little bit of trial and error as well.
Okay, great, thanks. So if there are any more questions? If not, then let's just thank Thomas again for the great talk. And the next Q-Farm seminar will be 2 weeks, and hopefully we'll see everybody there.
Thank you very much.
Great, thanks.